Okay, so last we left off, we were looking at the basic properties of the definite integral, which is an integral with bounds on it, numbers that we're evaluating from. So this is just the area under the curve. So we saw a few basic examples where if the bounds are the same, we just get a 0. If the bounds are flipped, we can flip them and change it to negative. If there's a constant in front, we can pull the constant out and then finish evaluating. So this one here, we have the integral from 12 to 17, but when I look at all of the things I was given, I have 11 to 12 and 11 to 17 for f of x, but I don't have 12 to 17. So what I need to look at is that, come on, Ben, there we go. If I have the bounds from 11 to 12, and then 12 to 17, and I add those two together, that equals the bounds from 11 to 17. Now, the one I want to find, though, is 12 to 17. So I'm going to subtract over my 11 to 12 integral. So this gives us the setup that the integral from 12 to 17 is the same as the integral from 11 to 17 minus the integral from 11 to 12. Now I know the integral from 11 to 17 is -9. And I know the integral from 11 to 12 is -3. And I figured out that I needed to subtract those. So -9 minus -3 becomes plus +3. So we end up with -6. So we're going about it this way, focusing on the bounds, because we don't know what f of x or g of x are. So we don't have a way to actually work out the integral. But this allows us to focus on some of the properties that we can make use of with the bounds, which do show up every once in a while in Cal 2. All right, I'm going to skip that combo one. So our definite integrals are areas under a curve. So if I have like 4x minus 4/9 times x minus 5, this is a straight line. A diagonal line. Goes through -5, and then it has a slope of 4/9. So it's pretty like that. So if I look at the values from 2 to 6, this actually creates a trapezoid that we could find the area of. I'm going to skip the actual hard work on that one, though. All right, this one here, a little more interesting. So the square root of 36 minus x squared, it turns out, is just the upper half of a circle. Now, actually trying to evaluate the integral of this, like this formula doesn't have a nice antiderivative. It's kind of a pain in the butt. We have to do trig substitution to do it by hand. But if we just remember that that graph is literally a semicircle, then I can just focus on the bounds for figuring out how much of this semicircle I'm shading in. So my first integral is focusing on the bounds from 0 to 6. So those bounds are x values. So I'm looking at x equals 0 over to x equals 6. So the area under the curve for those bounds is a fourth of a circle. So our area formula is a fourth of pi r squared. Now our radius of the circle here is 6. So I get 1/4 times pi times 6 squared. So I end up with 9 pi. Now, when I stretch the bounds to go from -6 to 6, that's all the way over here at -6 on the x-axis, all the way to +6. So that ends up being all of the area under the curve, which is just half of a circle. So half of pi r squared, half of pi times 6 squared is 18 pi. Now, later on in Cal 2, you will learn how to do this one without using the area formula. But for some of the graphs, just graphing it and realizing it's a basic shape that we can exploit some geometry on, we can evaluate integrals this way. All right, this one is an absolute value. It's a little bit weirder. More than a little bit weirder. That actually goes across the cornering point of the absolute value, so it creates two triangles. Ugh. Which my brain is like, no, I'm not doing that right now. Because to be honest, most of the time we don't actually bother looking at the graphs and figuring out the area based on the shape. Because most of those basic shape ones, we can just use the fundamental theorem of calculus, which is what our next section is about, our last section. So we've been looking at a whole lot of crazy, what feels very different concepts. We saw the Riemann sum is the same as the definite integral. We learned that the indefinite integral is equal to the antiderivative. So it turns out when I'm looking at the area under the curve, if I look at the integral from some constant value to x of f of t dt, that area under the curve, and if I wanted to know what the derivative of this was, as silly as this sounds. So if I have the integral from a to x of some function, not in terms of x, and I want to know what f of x is, then I can take the derivative of both sides of this, and the derivative of the integral ends up being f of x. So if I'm told that g of x is this antiderivative, the integral from 10 to x of this function, and all they ask for is g prime of x, then we have a shortcut formula we can use. So g prime of x is really just saying find the derivative of g with respect to x. So this is just asking us to do the derivative with respect to x of both sides of our function. Now, derivative and integrals, it turns out, are inverse operations of each other. They undo each other. So as long as what I'm taking the derivative of matches that variable on the integral at the top, then my result is just whatever function formula I had inside the integral, but with x in place of the variable. But all in all, what the first part of the fundamental theorem of calculus establishes is that derivatives and integrals are inverse operations of each other. They undo each other. Now we have to be a little more careful about that undo process because the integral has bounds on it. But in a very general sense, they do undo each other. Then we got the weird, but what if the bound isn't just x? So we can still work this out. The derivative of the antiderivative, the derivative of the integral, they are still going to effectively cancel each other out. But because I'm doing a derivative and I've got a weird function, I'm going to end up with the chain rule coming into play. So if I think of that sine x as a u, then my derivative with respect to x of this thing is, I'm going to plug the u in, and then I'm going to have it times du dx. So we're going to end up with the square root of 1 minus sine of x squared. And then we have times the derivative of sine of x. Now the derivative of sine of x is cosine of x. And then strangely enough, our 1 minus sine squared, that's actually cosine squared. And then the square root of cosine squared is just cosine. So we do actually end up with a simplified result of cosine squared x. But for the purposes of answering what they asked us, we could have just stopped there. The square root of 1 minus sine squared x times cosine x. So this sounds like it's a really big deal because it's called the fundamental theorem of calculus, but this isn't really the version we use that often. This is the version that we actually use all the time. So if I'm looking at a definite integral over the bounds from a to b of a function, then this definite integral is the same as the antiderivative evaluated at b minus the antiderivative evaluated at a. So if we do a whole lot of ridiculous work in general terms with the Riemann sum, we will end up with the antiderivative formula evaluated at b minus evaluated at a. So this is how we usually find the area under a curve. But this does make the assumption that I can find that antiderivative. So for right now, for the end of Cal 1, we're only going to look at very basic functions that we know the antiderivative of. Or that we can get in a form that we can do the antiderivative of. So we've got it split into two parts. So at the bottom, we're being asked to evaluate the integral from -2 to 2. But first, we're just being asked to figure out the integral in general terms, to figure out what the antiderivative formula is. So right now, I have a product. And I don't have a rule for an antiderivative of a product yet. So in order to do this antiderivative, I need to multiply those two things together. So we're still going to have our integral, but now we're going to FOIL this out. So I see 11x squared minus x to the fourth minus 99 plus 9x squared. All right, a little bit of cleanup. We end up with 20x squared minus x to the fourth and minus 99. Now, I still haven't done any calculus. That was just some algebra cleanup. So now the calculus is we're going to do the antiderivative. Now, these are just polynomial terms. So the antiderivative is just going to be our backwards power rule. So remember, our normal derivative, the power comes down and we subtract 1. So when we're doing that process inside out and backwards, we're going to add 1 and divide by it. So I keep my 20, that's just a constant. X squared is going to become x to the 2 plus 1, and then I divide by that new power. My x to the fourth is going to become x to the 4 plus 1, and I divide by that resulting power. Now the 99, the constant, has an invisible x to the 0. So then I can rewrite that as x to the 0 plus 1 divided by 0 plus 1. And then the last thing on my antiderivative is that there could be some arbitrary constant term. Now, since we're about to shove some numbers into this formula, I'm going to go to the effort to clean it up some. So this is 20 over 3 times x to the third minus 1/5 x to the fifth minus 99x plus c. So a whole lot of work to get my antiderivative formula. Now that I have that antiderivative formula, though, now I can actually do my definite bounds on the integral. So our fundamental theorem of calculus tells us this is going to be antiderivative evaluated at 2 minus antiderivative evaluated at -2. So I'm going to take that function that I just found up here. That is my antiderivative formula. So now I'm going to take 2, plug it into that whole thing, and then I'm going to take -2, plug it into that whole thing, and then subtract the results. All right, so there's my f of 2. Minus, now we're going to do f of -2. Can't forget the negatives. So this whole thing is going to be some big ugly number. But that c that I had, that arbitrary constant, I end up subtracting the constant off because I had c from the first one minus the c in the second one. It's the same c. So when we're doing a definite integral, the arbitrary constant actually gets canceled out. So we usually don't even bother writing it because it always gets canceled out in a definite integral. So all I have to do now is just do the calculation. Penguin Street. Now, if this was a problem on WebWork, you can just literally type in that disgusting expression without the C's, and WebWork will take it. And the calculator, because it'll do fractions, spits out negative 4,532/15. Which is why most of the time, like getting the final numeric answer is like meh. Like, yay, it equals a number.
On the test, are we going to consider the former? Do you like us to calculate the?
I'm not sure exactly how this shows up on the final. Like, I have to think about it. Hold on. Which means I actually have to go find it in my inbox.
How much of the test is the intervals?
So right now, it looks like it's 9 questions, 2 from exam 1, 2 from exam 2, 2 from exam 3, so that's 6 of them, and then 3 from the result. One of them is going to be a Riemann sum, which is but it's only going to be not the full do the limit. It's just like figure out the 4 rectangles, figure out the area and all that. And I did just make a writing assignment that is the same question format. Not that. So on the test, there are some indefinite integrals and then the same integrals but definite. But you can just round the answer to the nearest hundredth. But the formulas on them are more basic. So they're not as fraction stupid as this one is. A little, but not as bad. And then the other one is an initial value problem, which is we give you the derivative, you have to find the antiderivative, and then we give you a value of the function so you can figure out what the C value is. So you can answer what the singular function is. But we should have some of those in the review as well. Certainly there were some of those in the homework. All right, so like this one, a little more straightforward. Because it's just like a single term, not a whole bunch of terms. So 2 over the square root of x. Well, I don't have a rule for quotients. So the first thing is to rewrite this. So it's x on the top of the fraction raised to a power. So initially, I know that square root of x is the same as x to the 1/2 power. But it's still in the bottom of the fraction. So when I move it up to the top of the fraction, it'll be x to the negative 1/2. Now that is still algebra. I haven't done any calculus yet. But now it's x to a power. Now I can use my antiderivative power rule. So the 2 in front is a constant, so that's just going to come out front. And then my power rule says I take the x to the power and I add 1. and divide by that result. And then, of course, we can't forget because this is an indefinite integral. So this needs a plus c. Now we're actually going to use that formula here in a second. So I'm going to go ahead and clean that up. So negative 1/2 plus 1 is positive 1/2. So I have this thing divided by 1/2 that ends up becoming times 2. So we actually end up with 4x to the 1/2 plus c. So the 2 divided by 1/2 ends up being 4. Now there is a weird notational way to kind of notate what happens with antiderivatives and definite integrals. So I just figured out my antiderivative formula. And then after that, I put this straight bar and I put my two numbers from the bounds on the antiderivative. So this bar here is saying plug in the top number minus plug in the bottom number. I only introduced this because you might see this notation show up in the book, and this is probably how your calculus professor will write it. Sometimes instead of a straight bar, they may make it a square bracket, whatever. Usually when we write the definite bounds, we don't even bother writing the plus c. But now I'm going to plug in those numbers. So I have 4 times 81 to the 1/2 with the plus c minus 4 times 16 to the 1/2 plus c. Now again, the c's are going to cancel out. So 81 to the 1/2 is 9. So I have 4 times 9 minus 4 times 16 to the 1/2 is 4. So 36 minus 16 is 20. So the area under 2 divided by the square root of x from 16 to 81 is 20 units. 20 square units. Sorry, it's an area. Now our next one throws some trig at us, which is a little bit like, now I have to think. But secant squared is the derivative of one of the trig functions. So even though initially this is like ew. Because it almost looks like it's supposed to be a chain rule setup, but turns out the derivative of tangent is secant squared. So when I know my derivative rules, I also know some antiderivative rules. If I apply an integral to both sides of this, I end up with the integral of secant squared. Technically, there'd be a dx here, is tangent. So my antiderivative of secant squared theta d theta is going to be tangent theta plus c. All right, now down here, they gave us some bounds to work with. They're kind of ugly bounds, but our calculator will handle them. So we are going to take tangent theta and evaluate it from 4 pi to 17 pi over 4. So this is the tangent of 17 pi over 4 minus the tangent of 4 pi. Now, in order to use the calculator here, I'm plugging in pi numbers. Those are radian numbers. So I need to make sure my calculator is in radians mode. So the tangent of 17 pi divided by 4 minus the tangent of 4 pi. And it turns out this is 1. So 17 pi over 4 is coterminal with pi over 4. At pi over 4, sine and cosine are the same. So tangent there is 1. And then 4 pi, that's coterminal with 0. Tangent of 0 is 0. So this is actually 1 minus 0, which equals 1. So it is a little weird to get an integer number, but it does happen. Normally, we'd expect to see like square rooty numbers, but all right, our next one's a little more interesting. So we are looking at the integral of 1 over 11t dt. So the 1 over 11t looks a little weird, but I can separate this into 2 fractions. So that 1 over 11t is the same as 1 over 11 times 1 over t. Now that 1 over 11 is a constant. So I'm just going to move it outside the integral. So I'm just going to have 1 over 11 in front of my answer. But now we have to remember, what is the antiderivative of 1 over t? So what function has a derivative that is 1 over t? Yep, natural log. So that's our rule we're remembering. So if I put my integral on both sides, the antiderivative of 1 over t dt is ln of t. And then I just keep that 1 over 11 in front. Now, because this was asking for the overall antiderivative formula, I also need that plus c. Now, I will say sometimes people will look at 1 over t and they'll rewrite it as t to the negative 1. And then they'll try to use the power rule, like the power rule antiderivative. So you would get t to the negative 1 plus 1 divided by negative 1 plus 1. But what is negative 1 plus 1? 0. So I wrote t to the 0, which is like a little weird, but okay, that has meaning. But then I wrote divided by 0. Oh, yeah, no, I can't divide by 0. So this is the one term that the power rule fails. So if you're ever like not paying attention and you do the power rule and you get a divide by 0, that's the like, oh, wait, rewind. This is the one power rule case that I don't use the power rule. So that means it's my natural log scenario. All right, so we've got our antiderivative formula. So 1 over 11 times the natural log of t. And then I'm going to evaluate this from 2 to 8. So I plug in those numbers and I get that result. And that result is not going to be a pretty answer, but if I want the decimal, I just type it in. And my decimal is 0.1260267 blah, blah, blah. So I'd round to however many decimal places WebWork would want. All right, so this is an example Christy left worked out in the notes that I also left worked out because it's an ugly example. But sine squared of theta, we don't have a function whose derivative is sine squared that we normally work with. So what we have to do is we have a formula over here. I took my cosine 2x formula and I took the format where it's 1 minus 2 sine squared of x, and I solved that for sine squared. I get this formula here. So it turns out sine squared is the same as 1/2 of 1 minus cosine 2 theta. So I make that substitution, And then I do my antiderivative. So I get my general form and then I plug in the weird pi numbers. And we actually get an answer that has a pi number and an other number in it. It's a really weird setup. So I think there's like one question in WebWork that might do this. So that's why the example is here. But that finishes out our fundamental theorem of calculus. All right, so in WebWork, we have let's see what it's actually called. The final exam practice problems. And when you click on that, you then go, oh my God, there's 50 problems. What the hell? So you do not have to do all 50 to get the 10 points, the bonus points on the final. You only have to do, I don't know if we decided on 30 or 35 of the problems. So if you get 35 of the problems right, you'll get a full 10 points. If you do a little bit less, I'll have to do some math and figure out what you get. So basically it means you're looking at like between 60 to 70% overall on the full list. That's what'll translate into 10 points. So you can pick and choose which problems you want to do. Now, remember, I said the final itself was only 9 problems. So this list has way more practice problems than what is going to be on the final.
We have a class Tuesday.
Yes, we still have class on Tuesday. Tuesday is the last day of classes. Yeah, we're just going to review. In fact, since we finished the notes, we may as well start reviewing. But before I do that, let me find it. So here is the last writing assignment. No, it's not due till Tuesday. So this is just asking you to do a Riemann sum. But it's split out into each of the steps. So you figure out the width of each of the rectangles. So I've given you the function here. I've also given you a picture of the function over the interval. So it's just walking you through step by step how to do the whole Riemann sum in a very basic setup. So the graph is there to give you like a frame of reference, a picture you can actually draw the rectangles on. So this is very similar in format to the ones we did in the notes. But let's go ahead and dig into some of these practice problems. All right, so our first one here has a very ridiculous graph. And it asks us about figuring out what the limits are from the left and the right of a whole bunch of different values. So this was very similar to question 1 on exam 1. but this is also going back to the basic definition of a limit. So when I'm looking at like the limit as x approaches 0 from the left versus 0 from the right versus 0 overall. So my left and my right have to agree for the limit overall to exist. So when I'm looking at the limit as x approaches 0 from the left, so my 0 from the left, that part of the graph is shooting down off the bottom of the screen. So that's down to negative infinity. So 0 from the left, negative INF. Now 0 from the right side is shooting up to positive infinity. But since my left and my right do not exist, the bottom tells me type DNE. Now, because we were getting infinities, this is technically it's a jump discontinuity because the left and the right sides don't agree. But if you called it an infinite discontinuity, like it's also that as well, because there's an asymptote there at 0. All right, let's see what the next one is. All right, so this one, when we were first learning about limits, like we had to do some weird algebra manipulation on this. But now we have other tools in our tool belt. We can actually use L'Hopital's rule now if it applies. So to see if it applies, my first step is to take the number, shove it in there, and see what happens. So I would have 7 times -1 squared plus 5 times -1 minus 2 over -1 plus 1. So I can see my bottom is definitely a 0. On top, -1 squared is positive, so I have 7 minus 5 minus 2. That gives me 0 on top as well. Since I got 0 over 0, I can use L'Hopital's rule. Now, L'Hopital's rule is not just arbitrarily take the derivative. It has to be a fraction form where we get 0 over 0 or infinity over infinity. When that's the case, then I can take the derivative of the top and the derivative of the bottom separate. So I keep my limit. So the derivative of the top, the derivative of 7x squared becomes 7 times 2x plus the derivative of 5x is just 5 minus the derivative of 2 is 0, so I'm not even going to bother writing it. And then on the bottom, the derivative of x is 1 plus the derivative of 1 is 0. So now that I have this set up, now I can plug the number in here. So I have 14 times -1, -14 plus 5 is -9. Now, since the top and the bottom, when I plugged in -1, they both gave me 0. That means the top factors, and one of the factors is x plus 1. So the other way to work this one is I could have factored the top, canceled out the x plus 1s, and then plugged in my -1 on the result. And I'd get the same -9 as my answer. So most of the weird algebra ones we did on exam 1, a lot of those we can use L'Hopital's rule on. Yep. Mhm. Okay. So we're definitely going to have a question that's just going to ask you to compute some derivatives. So this one here, a little ugly, but workable. We got to remember our trig derivatives, but this setup here is also a product rule. So I'm doing my derivative of this. Now I could multiply the sine x through, but then I'm still going to have a product rule. So when that's the case, I usually just, I'm like, I'll just do the product rule from the start. All right, so when we're doing our derivative of a product, this is where I do the derivative of one, keep the other the same, plus, and then I do it the other way around, vice versa. So I'm going to do my derivative of A. So it's going to be A prime B plus AB prime. Like that's the way I usually write it. So our derivative of A, the derivative of a constant is 0, plus the 9 in front is just going to carry through. But now I've got to remember my derivative of secant. But so derivative of secant has a secant in it, but it's got to be just more than the function itself. And the two functions that always show up together are secant and tangent. So the derivative of secant is secant x tangent x. Now all of that is just A prime. Times B, B is just sine x. All right, now I keep A the same. -5 plus 9 secant x times my derivative of sine x is cosine x. Done. Don't try to simplify it. So as far as web work goes, just type that in. You don't have to write the 0 plus if you want. So if you want to take that part out for your typing, sure. But that's the only thing I would like bother cleaning up, only because I'm lazy and I don't want to type 0 plus. So when you get these questions that are just giving you a function and asking for the derivative, all you have to do is the derivative. Don't do any of the algebra cleanup. That's just a waste of time. It's easiest for me to grade it this way, so leave it this way. All right, here's a ridiculous one. So I have f of x is the sine of x to the 6 times e to the 8x. So I have a chain rule that is then going to have a product rule that is then going to have another chain rule. So the more practice you've gotten on doing your derivatives and using all the rules, especially using the rules together, the more quickly this part of the test will go for you, the more comfortable you are dissecting the setup. All right, so this is sine of ugly. So my derivative of sine of ugly is cosine of ugly times the derivative of ugly. Now my ugly here is x to the 6th times e to the 8x. So my u creates a product rule. So I'm going to figure out du dx. I'm going to have my a prime b plus ab prime. So a prime, derivative of x to the 6th, is my basic power rule. So 6 x to the 5th. That's my derivative, so I keep the other one the same. Plus, now I keep the first one, x to the 6th, times my derivative of e to the 8x. Now, the derivative of e to the 8x, e to the anything, derivative is just e to the anything. But if my anything is more than just an x, it provokes another chain rule. So this derivative is e to the 8x times the derivative of 8x is just 8. So I've got a whole crazy expression for du dx. I've got a whole crazy expression for the original derivative. So df dx is cosine of ugly times the derivative of ugly. Now the derivative of ugly is long, so I'm going to move this down. Give it some nice big parentheses. So 6x to the 5th times e to the 8x plus x to the 6th times e to the 8x times 8. And that's it. My stuff, from my du dx, these are not like terms. X to the 5th with my e to the ugly versus x to the 6th with my e to the ugly. Those are different. I can't combine them. So that's all she wrote for that. Yeah, you could write the 8. I'd normally write it like in front of the x to the 6th, so it'd be plus 8 x to the 6th e to the 8x. But if you wrote x to the 6th times 8 e to the 8x, that's fine. All right, this one's not bad. So overall, this question is asking us to evaluate the limit as x approaches 5 from the right of this fraction. But the question format breaks it apart. It wants us to evaluate the limit of the top and the limit of the bottom separate. So I plug in my 5. 5 minus 5 is 0. So I get 11 times the sine of 0. Sine of 0 is 0, though, so this is really just 0. Now on my bottom, I plug in my 5. 11 times 5 minus 5. That is 11 times 0, which is 0. So the quotient of those two limits is 0 over 0. So that 0 over 0 is the indeterminate form. And that is a form that we can apply L'Hopital's rule. So now we're going to evaluate the limit, but we determined the 0 over 0. So now I can use L'Hopital's. So I do the derivative of the top on its own, and then the derivative of the bottom on its own. I still have my limit. The limit as x approaches 5 from the right. On top, that will be 11 times the derivative of sine is cosine of whatever was inside. And then technically, there's times the derivative of the inside. The derivative of x is 1 minus the derivative of 5 as a constant is 0. So my chain rule, we end up with a times 1, which you don't even have to write. On the bottom, I have 11 times the derivative of x minus 5 is 1 minus 0. So I end up with just 11. So now we just end up plugging in the 5. So 11 times the cosine of 5 minus 5 divided by 11. So the cosine of 0 is 1. And then the 11s actually ended up canceling. So we actually get 1 as the answer to the overall limit after we use L'Hopital's rule. So in order to use L'Hopital's rule on the test, you need to show me that you got 0 over 0 or infinity over infinity. But once you've shown that, then you can just do derivative of the top, derivative of the bottom, plug in the number, and that should be all you need to do.